One interesting application of magnetism is magnetic resonance imagery, or what's called in the scientific arena nuclear magnetic resonance. Now, MRI is based on properties of the hydrogen nucleus. That's why in the same scientific field is called NMR, nuclear magnetic resonance, or NMR, because it focuses on the nucleus of a hydrogen atom, which is a proton. A proton is going to have a spin, like electrons have spin, and the idea is, with nuclear magnetic resonance, we are going to be able to detect the density of protons that's available in various tissues. There is a neat simulations. The pictures are from that simulation that illustrates that. Now, normally, all of our tissues have water, they have hydrogen. Now, all of these hydrogen protons are going to spin randomly, or like the text here says, willy-nilly. So all the protons are going to spin like this, random. Now, when we position a person to have an MRI taken, we position them in the middle of a strong magnet, in the middle of a solenoid. The difference then from the solenoid that I showed in lecture is the fact that this solenoid is going to be made up with a superconducting coil, meaning it's not going to have a core inside, but the wires themselves are not going to lose energy. So you are going to have a continuous current through them, and that's going to allow for a very large magnetic field. Now, when we subject that person to a magnetic field, okay, let's turn this on. This is what's going to happen. What's going to happen is these spins, or these small proton magnets, are going to align either parallel to the magnetic field or perpendicular to the magnetic field. Ideally, what's going to happen is you expect the same number of magnets or protons to align along the external applied magnetic field as the ones that are going to align opposite to it. However, what's going to happen, you are going to have more of them aligning in the lower energy state. More of them aligning, as you notice here, with the north on top. And we have the extra ones here highlighted purposely to show us. Now, in magnetic resonance imaging, what we do is, once we create this alignment, we subject the person or the tissue to a radio wave frequency, RF, a radio frequency pulse. Now, that's the same frequency as the frequency we use to detect radio signals or TV signals, the same range of frequencies. But we send a particular radio frequency signal that corresponds to the energy needed to get these to flip. So when we do that, they are going to flip. But then you notice that immediately after the pulse is over, they flip back. And once they flip back, what do? They give off that excess energy. And that's what we detect, that excess energy. Now, various tissues are going to have various concentrations of hydrogen, so they are going to have a different percentage of these hydrogen atoms that are going to absorb the radio frequency energy. And by measuring the emitted radio frequency by the hydrogens, we can know how much of the hydrogen is in that tissue. And the percentage of hydrogen is the signature of that particular tissue. It tells us what kind of tissue it is.